Hello and welcome to today's Wolfram Institute live stream. We're joined with Giacomo Bocchese and Etienne Guichard, AI researchers. Giacomo, can you introduce Etienne and we'll get started?
Yeah, Etienne is doing a very cool work about using neural cellular automata to tackle the ARC-AGI problem. He's an artificial life researcher. He is collaborating with us at Prestar Labs, and yeah, his work is very cool because was able to get excellent results with very small neural networks that imitate cellular automatons. So I leave him to speak, and everyone, let's enjoy this.
Thank you, Giacomo. Yeah, I was originally going to just present the ARC-NCA paper, but I thought maybe some background would also be nice on the sort of predecessor architecture that came before this, called EngramNCA. So this is more of a talk of EngramNCA to ARC-NCA, and then also the results of ARC-NCA. So the first model was called EngramNCA. It was ostensibly modeled on some new research done in what's it called, the neurobiology space, where there are some theories about RNA possibly affecting memories and affecting where engrams are stored. I will talk also about it in a more computational sense as well, but it was a neural cellular automata model for memory transfer effectively. I'll sort of present the original neural cellular automata first by Morgenstern et al. Called Growing Neural Cellular Automata. So in this paper, they effectively have a CA where the rules can be learnt. It's usually comprised of a bunch of filters, and then the output vector for each cell is passed to a feed-forward neural network, or as is often implemented, a one-by-one convolution, since they're equivalent. Then that produces a partial update, delta S, that gets added to the previous step N. So it's sort of like a leaky, deep convolutional neural network that only sees like local neighborhoods via convolution filters. And in the original paper, they also just try and grow shapes out of a single seed. So this is the architecture here. Now, the idea for EngramNCA was, at least for standard neural cellular automatas, one set of parameters, so one set of neural networks, gave you sort of one set of genetics. So you want to grow a lizard, you have to train a neural cellular automata. You want to grow a butterfly, you have to train a new one from scratch to grow a butterfly. We wanted to move from this CA parameters equals sort of genetics view to the CA parameters is the world's physics view. So we would train one CA to learn computational primitives, or the physics, and then train a secondary CA to exploit those primitives. And then we tested on a classic morphogenesis problem, so growing the lizard. Another view of this is CAs can be seen as Turing machines as well. And so the tape encodes the program. So one CA learns, give us outputs conditioned on a program, and a secondary CA learns to manipulate the program to change the outputs. So these are sort of codependent CAs, one dependent on the program and one dependent on the output to change the program. Our method was quite simple. The first CA was trained with some private vector embeddings. So these are extensions to the hidden channels of the CA, so the ones that aren't displayed, that are untouchable. So it can't modify the program. And then through those embeddings, we usually used binary embeddings. So yeah, we used binary embeddings. You could sort of program what the cell would grow. And this is not limited to simple shapes. We also chopped up the lizard and gave each body part an embedding. And the architecture is very similar to the standard NCA. It goes actually through the same update steps of seeing all the channels, going through fixed convolutions, Sorbels and Laplacians, and the cell identity, and then through a feed-forward neural network. It's just at the end, the update vector, we take the private vector embeddings, and we just concatenate them back at the end. So it produces only a partial update, so it doesn't touch the private embeddings. And then we just concatenate them back, so there's no change to the private vectors. The secondary CA, the gene prop CA, is the same but inverted. So it gets to see everything. It produces a partial update, but only to the private vector embeddings. It cannot touch the state, the hidden state or the visual state. It can only touch the private vector embeddings or the program. And the entire model is an ensemble. So at step N, you have that current step. You pass it through the gene CA, the first one that only messes with the visible and private channels. To get an intermediate update, that intermediate update is passed to the gene propagation CA, which only messes with the private vector embeddings, and then that gives you step N+1. So they work sequentially with each other and together. For training, it's also very similar to the original neural cellular automata, which is you have a pool of states. After n update steps, you backpropagate on with L2 batch loss, and then you update the pool with your new steps, and every time you sample from the pool without replacement. The only difference here is that for every shape we maintain a separate pool, and the batch size is such that it's always a multiple of the number of shapes. So if you have 3 shapes, the batch size is 9, and so in the batch you see 3 examples for each shape. The gene prop CA is also trained in the same way. Now, because we're training only on one morphology, you only have one pool, although you can expand this to train on multiple morphologies. I'll explain that later. So same as the classical neural cellular automata. However, the gene CA, so the first one, their parameters are frozen. So it is now stuck in stone. It can produce the primitives, so say the shapes you see here, based on the embeddings. And now it's up to the gene CA to learn via the gradients of the gene CA and its own gradients how to update the private vector embeddings so as to grow a different shape than the 3 that were originally trained. So here's some results on, this is just a gene CA. So this is private vector embeddings. As you can see, on the top here, you have the actual value of the embeddings and the shape that's being grown. So you can indeed encode multiple shapes into one CA. This is not a problem. You also get some interesting untrained behavior. So if you actually mix the embeddings, you get sort of almost expected mixed shapes. So as you can see here, this is a mix between a blue square and a red triangle, and this is a mix between a red triangle and a green circle. This is fully untrained. We did not expect this to happen. We just wanted to see if it would. And yeah, it somehow does. You also get another untrained behavior, which is individuality or strong boundary between behaviors. So you can start placing these wherever you want. And they'll sort of grow and form boundaries. You can see here a boundary between the 2 greens and the green and the blue. Again, if you use a normal neural cellular automata and you try placing 2 objects together that you've grown, they will eventually merge and sort of mess with the structure overall. So this is novel behavior and unexpected. So once the gene prop CA is trained, what you could do is then train it to grow a more complex morphology by mixing in the same way that these are being mixed here, the vector embeddings. So on the left here, you have it growing from a torso. So we embedded just all the lizard parts, and its task was effectively to stitch the lizard together from all the embeddings. And on the right, you have it growing from basic shapes. So the embeddings only encode for 3 RGB shapes, and it has to mix them in a more complex manner, obviously, to grow. And what you can see here as well is that it was trained to grow only from the blue square. And so if you start with a blue square and a green circle, it'll grow the lizard from the blue square. From the green circle, it won't. Now, this can actually be extended.
Is that just a feature of what was being placed there before, or are those 2 lizards like competing with each other and one wins out?
No, they're not competing. If you placed 2 blue squares, you'd have two lizards. They'd be they'd inhabit the same space. Yeah, no problem in that. This is just because it was trained to grow from a certain shape, the blue square. So when you try and grow it from a green circle or say a red triangle, It's not trained to do that, so it sort of just disappears. It dissipates itself.
Okay.
Now, this can actually be extended. So if you take this idea of private vector embeddings that can't be touched, you can append another layer of private vector embeddings that is untouched by both the gene CA and the gene propagation CA. And now you can encode for multiple larger morphologies. So you have encodings for small morphologies, such as the square, triangle, and circle, and then embeddings for larger morphologies, such as a lizard or a butterfly. Here the quality decreases, but this is because we kept the network sizes the same. And as you try and pack more and more information, it sort of gets worse at reconstruction, since it's probably running out of parameters to make a good reconstruction. Finally, I want to talk about a little experiment we did with moving morphologies. So on the left is a Lenya system. I hope most of you know what Lenya is. If you don't, please go look it up. It's very interesting. Just a video recording of a Lenya system that is not arbitrary. So not just a translation across space. It has this like oscillating motion that is hard to replicate. In the middle, we have a standard NCA, and in the right, the gene CA. They were both trained using the same method. So this was a curriculum style training where they're trained to first grow the first frame. And then once the loss gets lower, we attach 10 more frames and so on and so forth until we get to the length of the video. Both CAs will learn up to the length of the video, but the center one, the standard CA, will start to make mistakes as soon as you're past the length of the video. So it's effectively memorizing the video, where the gene CA seems to learn more general rules to sort of the dynamics of the Lenya world. And so you can actually run it for longer, and it just keeps this oscillatory motion. It's not perfect, obviously, but it does seem to work. So a little conclusion on this. So we can train many behaviors in one model. Then we can train a separate model to exploit those behaviors to get more complicated behavior. The models present desirable untrained characteristics on top of their trained ones, such as out-of-training generative capabilities, strong untrained regenerative capabilities, and strong boundaries between behaviors. So this sort of led us to think, what can we do with this? And my PI was insistent on trying it on ARC. So this is how we got the ARC-NCA towards developmental solutions to the abstraction and reasoning corpus. A brief introduction to ARC problems. It's a reasoning benchmark, and I'm talking about ARC-AGI 1. By the time we published this, ARC-AGI 2 came out like a week after, and then ARC-AGI 3 a month after that. So ARC-AGI 1 is a reasoning benchmark. It's a few-shot learning benchmark, so usually you get 3, maximum 4 examples per task, sometimes even 2. It's quite simple for human, since it actually exploits a lot of our biases, but very hard for current machine learning. And the technicalities are, it's always a grid with 10 states at most. So there's a possibility of 10 states. You often see no more than 4 or 5. Again, the problems make heavy use of human priors, and you get 2 attempts per problem as in terms of machine learning systems. So you get 2 shots at it. So why not traditional deep learning? Effectively for this, at least in my opinion, mappings are ineffective for reasoning. We even see this with modern LLM methods with the extra generation of tokens with what they use right now. Instead of a single shot to get the answer, they let them think for longer. It's almost effectively trying to implement recursion without actually implementing recursion within the model. Deep learning requires a huge amount of data to train from scratch, and models with enough human priors, so LLMs, for example, are hugely expensive to run. So for ARC problems, this can be quite, well, it's not quite expensive, it is expensive. In terms of the potential for neural cellular automatas, and this is on the technical side, they're small but expressive, so they tend to often occupy fewer parameters than equally expressive feed-forward neural networks. They're a subset of all cellular automata, some known to be Turing complete, so neural cellular automatas could be Turing complete. They generate their own training data, funnily enough, and if any of you have seen the recent discourse with HRMs and the ARC Prize, The ARC Foundation effectively found that their model had very little to do with the performance gain, and it was more their training regime, how they augmented, and also the fact that the model got to see a lot of intermediary steps. So it got to correct mistakes along the way. And NCAs, with their pooling method of training, effectively do the same thing. They generate intermediary steps. They get to explore a large state space before coming to an answer. Their trajectories, so recurrent over mappings, which allows you to correct mid-trajectory or instead of in one shot, attempting to get the answer. And the state affects the computation. So they self-modify in the forward pass. This has the potential for gradient-free meta-learning. We're not there yet, but I do believe it might be possible. Then the potential neural cellular automata on the practical side. NCAs are already formatted as a grid, so ARC translates quite well to them. They're used to simulate biological phenomena, which is also very relevant to a lot of ARC problems. They're cheap and fast to train with backpropagation, and it's a novel and unexplored topic, so it was worth exploring. So in the paper, we used 4 or 5 different models, but we really only present 4 different models. The standard NCA with no augmentations, and then Ngram V1, V2, V3, and V4. We omit V2 since its scores are not different enough from V1 to be presentable, and we had limited space, to be honest, for the A-Live conference we were presenting at, so we just omitted it from the results. Just know that they're very similar to V1. And on the right, you have the channel size. So the CA has 50 channels, and the hidden dimensions. The standard NCA has 64 hidden DIMs in the feed-forward neural network, and the Ngram V1 has 32 and 32. So because it's a dual model, both of them get 32. I'll go over the augmentations on this slide. So you can see here in the middle column, we have augmentations. They're called sensing, toroidal, and local versus global. The sensing one is effectively the standard NCA has set convolution filters. So for the Ngram, say V2, V3, and V4, we let it learn its own filters. Since the biases introduced via the standard Sobel and Laplacian might not be correct for every ARC problem. The toroidal augmentation, standard NCAs are toroidal. They're translationally invariant. You could place the lizard wherever you want. It'll go fine. It doesn't actually know where the edge of the world is since it lives in a toroidal world. This is fine for some ARC problems, but some of them need a hard boundary. Or else, in a toroidal world, you just don't know where to stop. So what we did here was we split it, since it's a dual model. You can have one model that's toroidal and one model that isn't toroidal. And then they can sort of select where to pay attention to, whether to use toroidal information or non-toroidal information to see if there's a boundary or not. And then the local versus global training, the regular L2 loss on the image sort of emphasizes a global loss on the image, but sometimes you want just very local behavior. So what we did was, on top of the global training, we would split the image up into patches, just 3x3 patches, and we would run the NCA on the 3x3 patches, and then get the loss and accumulate the loss on that as well, so that it would learn both global behavior and then strong local interactions. And we also gave it a local form of attention. So this was channel-wise attention. So each cell can attend to its own channels. Some other technicalities. So this is from ARC to NCA. There are many ways to do this. This was a basically an arbitrary choice. There's another paper that I'll go on to talk about later that made another arbitrary choice and yet got the similar results to us. So this is from 2D integer grid, which is the ARC problems, to 3D real valued lattices, so a neural cellular automata lattice. What we did was we took the integers, mapped 0 to 9, and mapped them to an HSL wheel. Now from that HSL wheel, you can get an RGB alpha value, and then the RGB alpha value can be the RGB alpha values of the image of the ARC problem. So when you visualize an ARC problem, this is almost effectively what you're doing. You're just mapping some integers into a color so you can see it as a human. Most machine learning problems either map it into a one-hot encoding or have the model learn the encoding. We just encode it into RGB. The other channels are filled with different representations of the ARC problem. So other channels are filled with things like binary encodings of the ARC problem or one-hot encodings of the ARC problem. This is just to sort of augment it a little, give the NCA a little more information it can start with. Then we also have dealing with changing grid sizes. The first experiments, we just ignored problems where the input grid was different from the output grid, since this happens in ARC problems. And NCAs don't have the ability to modify their own grid size. In other experiments, what we did was effectively pad every problem to a maximum size of 32 by 32 with a special padding token, and then allow the NCA to modify the padding tokens and then clip all the way down to a minimum square or rectangular boundary. So it could effectively change its own size. And this is what we're doing is effectively a program synthesis approach. So for every ARC problem, we actually generate a new NCA from scratch. The NCA training loop can be seen as the program generator. And for each problem, we generate a new NCA. Training only on the 3 examples given in the ARC dataset, or 2 or 4, however many there are for that problem. After training, we evaluate on just the evaluation problem. So this is pure program synthesis with almost no priors in there. It's just starting from 0 every time. The training loop is slightly different from the standard GNCA GeneProp-CA. So previously with the GNCA GeneProp-CA, what we did is we trained the GNCA to be dependent on memory, and then change that memory to induce different behavior. However, with ARC, we don't know what those dependencies should be. So instead, what we do is we train them together. We co-optimize them. So they learn to both generate and modify the program and react to the program at the same time, instead of attempting to train priors into the GNCA and having the GeneProp-CA learn how to modify those priors, since there's no way of knowing what those priors are at the beginning of an ARC problem. Some general notes on the results. As you can see, all the problems seem to grow into place. This is just a feature of neural cellular automata. Since they're local, they can't do a global one-shot update. So all the problems will look like they're growing. Yeah, so on to the results. With these images, what you'll see is the solution to the evaluation problem, and then 2 examples of the training problems. So these were interesting, just sort of out of the techniques they use to grow. So this one, the problem is quite simple. So you have all these purple dots, and you have to connect them with straight lines. And if you can't connect them with straight lines, you leave them unconnected. And here, what you can see is the NCA starts growing in different directions from the dots, even extending further. And then if it doesn't find a connection, it just retracts. And there you go, it solves. On this one, so what you have is this yellow line, and upwards you just have to grow in increasingly long steps, green lines, and decreasing downwards, decreasingly short steps, orange lines. So this one, it effectively just grows it almost like a pyramid or a tree, or just like dripping water. These type of problems seem to be quite easy for NCAs, where almost growing is inherent in the problem itself. This one's a bit more interesting. This is effectively a filling problem. You start with lines. The lines can be any color, any arbitrary color. And then you have to infill anything that's enclosed by these lines with the yellow color, and infill anything that isn't enclosed with the green color. So here you can see it starts by just expanding green everywhere. So it just does a quick infill. This gets you most of the way to the loss when you're comparing images. And then it refines. It's hard to know exactly how, but it refines by probably checking boundaries within these boxes and then changing the color. Sorry, one last note on, the general notes. Sometimes you'll notice that the colors aren't exact. This still produces a valid ARC problem, ARC solution. Since we're mapping to an HSL wheel, you effectively have color buckets. So the color doesn't need to be exact. So here, this purple here, and this purple here, effectively map to the same integer when you transform this back into an ARC problem. Because of this, we actually found a minimum bound loss for what you could consider a solved problem. So if you take the log loss, the natural log loss in RGB space, if it was lower than -7, you could effectively map it back to an ARC problem and have no loss. And because you're using L2 image loss, it's very common or almost guaranteed that this slight loss is spread over the entire image and it's not just concentrated in one pixel. Yeah. So on the results, on the left here, we have just, so the mean loss overall problems. So yeah, overall 400 problems, or 262 if we're ignoring any that change size. And the solve rates on the ARC problems. So yeah, the worst one was V1. And the best one was EngramV3 with most of the augmentations, but not all of them. And yeah, what's nice to see is that it compares quite well to ChatGPT 4.5, which is, well, at the time when we did this, the best model that did not use chain of thought. That was just one shot. And because you're allowed to attempt twice, we decided to check what the unions of these models would be. Since for each problem, we can just run 2 different models. So we wanted to see which ones were the best unions. For here, the best union was the V1 and V3. So even though V1 was worse in terms of the solve rate, it solved enough different problems to V3 that when in union with V3, you can get the most amount of problems solved. And V1 and V4 must have had a very large overlap because it doesn't increase V4's solve rate by that much. Now onto some other interesting bits. We had partial solutions, which is something you can have with a trajectory of solutions. Here in this one, what's effectively, so the problem is effectively just infill any of the lines that go edge to edge, even if they cross, and anything that doesn't go edge to edge, you do not infill. On this one, we believe it was sort of an edge case problem where we, in the evaluation problem, there's very large gaps here, in the one at the edge here, one in the center here, which were not seen in the training problems. And so it didn't generalize that well. So it got quite close. This one, however, what's interesting about this one is that it actually does go through. So if I stop it here, oops. Yeah, so this is effectively a flower growing problem. This is perfect for neural cellular automatas. It's growing from seeds, the same thing as the original did. And what happens here is it actually passes through the solution. So this is where I've frozen it here. This is an exact solution. This would have gotten you a solve in the ARC prize. But because we don't know when to stop an NCA, we don't have a stopping condition. We just let them run for an arbitrary length of time, usually 8 times the training steps. The NCAs have to learn to stabilize in a state. And here it is sort of gone through the correct state and then overshot, and then it learns to stabilize in this wrong state. Now, this gives us some hope because these are very minor issues. There's a single pixel off, and here there's like maybe 3 pixels off. So we wanted to check how many of these problems did we have that are like sort of easy to fix, or at least theoretically easy to fix, because we're very close to the solution. And so we loosened the threshold to a log loss of -6, which was the loss for all these minor error problems. Here, EngramV4 was doing the best, but you can see you have some good margin. So EngramV4 was 10% before, now it's at 16%. So in theory, we have 6% to gain just from some minor improvements. And the same thing with the unions here. We have about 6% to gain just from minor improvements. I also wanted to talk about the costs. These things are really cheap to train. So I trained them at home on a RTX 470 or RTX 470 Ti. It has 12 gigabytes of RAM. I never used up to 12 gigabytes. For the entire data set, it took about a day to train. The cost you see here for both training and inference, the cost for LLMs like ChatGPT 4.5, that is just inference. So it's already been pre-trained or trained. They might do a little bit of fine-tuning as well. They're not very specific about it sometimes, but I think it was just inference. And then NCA's inference only is vastly cheaper, like a few orders of magnitude cheaper again than just training an inference. So as an example, training on a large problem will use about, so this is large in terms of grid size, we'll use about 10 gigabytes of VRAM. When you actually run it in forward pass, it's about 200 megabytes of VRAM that you need, since you're not accumulating gradients over recurrence and with long-range dependencies. Another part of the results we had was reasoning pitfalls, or what I would call partial reasoning. So in this problem, you have on the left of the line, you have a shape that you have to grow on the dots. The reason we say this is partial reasoning is because the dots do change in position. So it didn't just memorize where to grow shapes. It does have to reason about where the shape should be grown. So it did that part correctly. However, it didn't reason on the part of you have to copy the shape exactly. I think the problem was too hard in terms of long-range dependencies for this to work. And you can actually see this square over here is an exact copy of one of the sort of input problems. So it sort of memorized the shapes instead of, or memorized the shapes and the colors where they should be instead of learning to just move the shapes to the right spot.
Interesting. It seemed like it memorized a incorrect shape. It's not a direct copy of the top left.
Bottom right. So this one.
Well, yeah. So there's that green like upside down H on that side, and then the other ones that were copied don't match exactly.
Don't match anything else. No.
Exactly.
I think so. Let's see. There. Yeah, so it might just be that this square here only appears in this problem. So on all the other training ones, it doesn't exist. So when it grows that one, it just grows this one because it only appears in this problem. And all of these might appear in different training examples. And so it's just sort of mixing the training examples. That was sort of my theory on it, that on the ones that there is overlap, it sort of mixes. Or yeah, something along those lines. And on the one where there wasn't any overlap, it just grew one that it knew. However, if you do look at them, these are all quite similar. So it is sort of growing a very, it is repeating a pattern, at least for most of them, except for that one. It's just not repeating the correct pattern. Again, because this is still a machine learning technique, like a deep learning technique. It's hard to know what it's doing. You can't very much reason about it. You can check the channels as well as the CA, but it tends not to give you a lot of information. Yeah, so the only thing I could call this is partial reasoning, and got one of the reasoning steps correct. The other one, who knows what it was doing. Yeah, so now on some further experiments. This was effectively an attempt to solve the minor errors that we were making before. So the question was, what if we just increase the dimension of the CA? So no longer 32 by 32, but 132 by 132, or sorry, 132 hidden dim. And we also just wanted to test it on just the maximally padded. So we just took V3, which was doing the best before, and we padded it to the maximum on one of them, and then the other one we just increased the number of hidden channels. And indeed, as I said before, you had about a 6% margin of increase that you could get, and this is basically what we got. So we got up to the 16% solve rates that you saw if you loosened the threshold for solving. So that's quite good. And this one costs, 5e to the minus 4 per task, so still really cheap, even though we've increased the dimensions. If you loosen the solve rate, so once again, check any of the ones that are almost solved. V3 padded actually gets quite a good solve rate. So again, this is sort of future looking, saying, okay, these are problems that are nearly solved. It probably requires a little bit of tweaking, and then we can get it solved. And before anybody asks, I did try increasing the dimensions even further, but it sort of hits a scaling law really quickly. Diminishing returns happen basically past 132, you're not getting much better. You're just getting memorization. It gets too big, and since there's only 3 problems, it just it starts just memorizing the problems because it has enough parameters to just memorize. Yeah. Some parallel work that was done to us. So this was published a month after ours, called Neural Cellular Automata for ARC-AGI, so extremely similar. Their encoding, so they did basically the same thing as us. They just only used the standard NCA, and they used one hot encoding for the problems. 10 channels for the CA, and then the CA just had to, make the channel 0 or 1, or they max clipped the CA channels. And what they did, which was interesting, was a more in-depth analysis of the capabilities of the NCA. What was particularly interesting was this one. So this is the spiral. These are the training inputs, training inputs and training outputs. You're effectively just growing a spiral based on a grid. And, sometimes the spiral is, the inside finish is green, and sometimes the bit that finishes on the inside is black. It just depends whether it's odd or even. Once they trained it, they had basically a perfect result. But they wanted to see what would happen if you expanded it. And so I believe this is 100 by 100. Yeah. And so if you did it for 100 by 100, it would generalize perfectly. So, and I believe they tested it for different sizes as well. And it basically didn't matter what size you used, it just generalized perfectly. And what they noted is that to produce a program that does that would actually be quite complicated, to search for a program that does that. And yet, when using a neural cellular automata method, it trains, every problem trains in a few minutes. Yeah, so on discussion. So the solve rates between 10 and 15% or 16% baseline. Padded versions improved partial success rate. So to 27%. So we're looking forward to maybe getting even 27%. It's extremely low compute, so minus E or 3e to the minus 4 to 7e to the minus 4 per task, so fractions of a cent instead of dollars. Its partial solutions indicate, promise for improvement via architectural tweaks. And the NCAs, they excel at iterative refinement and emergent reasoning, but they struggle with fine-grained details often. Novel edge cases, like most machine learning algorithms, and more importantly, long-range dependencies. That is sort of the major bottleneck of neural cellular automatas. Since they're fully local, if you have a grid that's 10 by 10, it takes a minimum of 10 steps for information to flow from left to right or from one end to the other, and more if you're going corner to corner. So and the issue is as they get bigger, and so for ARC-AGI 2, where the grids are much bigger, you have to run them for longer, and so you do start to encounter vanishing gradient problems because they're effectively recurrent neural networks. Some critique, since this is going to a conference as well, and we've had critiques from the conference. We use the public evaluation set instead of the private test set, since we don't have access to it, and we didn't actually send it to the ARC prize. They say risking unintentional bias. This was one of the critiques. Since we're doing a pure program synthesis, there's probably no bias in there. I think what they meant was that a lot of the problems are similar-ish. And so if the NCA was good at solving one type of problem, it was very good at solving all those type of problems. The experiments are effectively on a different benchmark than ChatGPT. That is true. We did just want to show that it could solve ARC problems at a similar-ish rate to a very large LLM at vastly lower cost. And the current approach trains a new NCA per problem, which is impressive for sort of a few-shot program synthesis thing, but it's unclear if it supports reasoning or generalization to novel tasks. Now, what the other paper did show is it does generalize the task of the same type, or So, it might not generalize to novel task, but if you have, it does generalize within the task set. Some further work, or where I think these NCAs could go for in terms of reasoning. The approach is effectively canonical. We just took the ARC grids and we turned them into CA grids, and then we ran a CA over them. It's probably the easiest way you could probably try solving ARC problems with NCAs. So there are some improvements to be done. I think one is to pre-train NCAs to develop priors that could help. So with the GeneCA, GeneProp-CA method, you could potentially train the GeneCA to be conditioned on a lot of sort of simpler priors, such as like move a pixel right, rotate a shape, and all of these things, and then only train the gene prop CA to combine those priors. You just have to sort of generate your own data set of ARC priors or extract them from the ARC dataset. Yeah, method that combines NCA for reasoning and image processing seem promising. So on the right here, I have some images on a paper done by some colleagues called Moving Sensors. So a quick overview, and then so an NCA has a convolution filter. In this case, what they did is they separated sort of the convolution, the sensing part, from the thinking part. So what the NCA does is it convolves over a pixel. This goes into gets inserted into an NCA that is effectively the neocortex. It then does an update step, and then it just tells the filter where to go. So instead of the convolution being, just left to right, pacing over, it can move the window. It can choose where it goes. And what they found is that with this method, where the NCA can select where its own sort of visual filter goes, it developed emergent attention. So this is, on the MNIST dataset, and this is MNIST fashion, and then this is like Sci-Fi 10. You can see where it focuses to look for each of the problems, which is very interesting. And again, it doesn't actually have an attention block. This is just emergent behavior of allowing it to move its own sensor. And another one would be sort of critical neural cellular automatas, like critical CAs as neocortexes. Since I'm sure a lot of you know, there's this theory that effectively critical CAs maybe all of them may be Turing complete. It's not known, but they may be Turing complete, in which case they could be more computationally expressive than standard NCAs that are generally not Turing complete. Well, that was it. Thank you for listening. Are there any questions? Usually I expect questions in the middle, but I guess people may have questions now.
So
Maybe from the YouTube video?
I had some questions.
Yeah.
So a lot of these seem to be like filling problems,
Yes, a lot of them are filling problems.
and with the gecko, that was like a filling problem as well. So it's like it memorizes primitives and then tries to push those into the image. So how well does it do on other types of reasoning tasks?
So do you mean on? Yeah, I mean, a lot of them seem to be filling problems. I think as well, just effectively on the way the NCA forms the images, it does also just look like it's only doing filling problems. So there's one, I don't have it here, but if you actually go look at the ARC-NCA paper that we published, we have a website as well linked in the paper to all of the solutions we got. So we effectively just dumped every single solution we got. And there's one of them that's sort of bouncing a ray of light, right? So as humans, we have this prior, we know how mirrors work, we know how reflections work. So it's a 90-degree bounce. It's very easy for us. For the NCA, funnily enough, what it does is it just keeps filling the line downwards and then it bounces. So yeah, a lot of them are filling problems. And so, but that's sort of what's interesting about ARC is that it has a lot of human priors, and a lot of human priors can be decomposed into sort of almost like a filling problem or just a path problem or all of these things. So it does quite well in those. Like I showed here, this is both a filling problem and also sort of a translation problem or like a long range visual problem. Yeah, so it struggles with that. It struggles a lot with rotation problems. So if it's just take an image and rotate it, that tends to be very problematic since it's especially with a 3x3 convolution, which is its sensor effectively, what it gets to see of the world. It's hard to do a nice, rotation. Like a 45-degree rotation on a 3x3 convolution doesn't give you a very good convolution filter. So it's hard to develop filters that do rotation properly when you have such a small convolution. Are there any problems I could show you other than, yeah, I mean, these are effectively growing. So yeah, same thing. This one's growing. This one's also just connecting edges, so very simple.
Would you mind bringing up that web page from the video gallery?
Yeah. Let me.
It's really cool. Really good stuff there.
Let's see, ARC-NCA. So that's the paper. So the video gallery should be. Here you go. Hopefully it loads. Can this be seen on the live stream?
Yes, yes, we can see it.
Yeah.
Yeah.
Okay, so these are solutions and partial solutions. Let's see. I mean, obviously, that's a filling problem. This one's a counting problem. It can do okay on counting problems if the edges are connected. This one's a transformation problem. So if you let it reload, there you go. But again, they all sort of like look like they're filling. Let's see if I can find anything like any of the ones that I find.
There was the one that grown the edges up and down and laterally, like one of the examples you shown before. That it's actually a search problem because it tries and then deletes the parts that exceed the shape.
So that would be So this one here, the purple one here, this one is, but it effectively decomposes the search problem into a growth problem. So, oops. It tries, it goes looking, and if it doesn't find, it just retracts. And with a lot of other ARC problems that are like that, sorry, it's, yeah, a lot of other ARC problems that are like that, it effectively, it's using the tools it has, which is it can only grow. It's an NCA. It only knows how to grow locally. So it's decomposing everything into effectively growth, retractions. So rotations are hard. So there's another one that was a translation here, this one. So you effectively just have to translate one to the right. Very simple as well. Or one down. The examples were either right or down. So it can translate simply, but it can't translate long range. I think so. This is a partial solution to, or maybe even a full solution. This is effectively denoising. But again, very simple for NCAs because it's you just look at your neighbors and match their color. So yeah, and then I think this one is edge or singular deletion. Yep. So if you're just in a lone cell, you get deleted. Again, very easy for an NCH. Check your neighbors. If your neighbors are, it's almost like Conway's Game of Life. You know, you could probably replicate that behavior with like a CA with like 5 rules. If you have any neighbors stay alive, or maybe even just 1 rule.
Yeah, it's like a consensus protocol.
Yeah, it's a consensus protocol. Check your neighbors. If there's any alive neighbors, stay alive. If they're not, die. That's it. You know, like it's a very simple rule. But I think this is just, I mean, I also think ARC is well suited to this, the sort of CAs, since it is grid based. If you look at ARC-2, I think that's a lot harder. I don't know if any of you have ever seen ARC-2.
For our audience, can you give an example? Can you go to the ARC placing these?
I tried solving it manually. It was difficult even for me as a human.
Yeah. Like as a human, it's like, okay. So this is an example. Okay, obviously this one's not too hard. So anything that has a singular hole, you color yellow. Anything that has, sorry, no hole, you color yellow. A singular hole, you color green. So, and by singular hole, it means like 1 opening. So even if it's too big, 2 holes blue, 3 holes red, right? But this starts to require like long range dependencies, chunking of the image. So like you have to understand this is your dependencies and this is your dependence. I think an NCA might be able to do this if it can propagate sort of information about holes all along, and then the shapes can check for holes. The reason I think that is because you have NCAs for MNIST. Let's see. Sorry, 1 second. I don't remember what it was called, but I do know how to get there. So this is the original paper. And then self-classifying MNIST digits. There you go. So this is really cool. You can effectively just draw an MNIST digit and it self-classifies. So the classifications are the colors here. Yes, let me speed it up. Yeah, it's not always good, but half right. Let's see, 3. Come on. Yeah, it's hard to reach a consensus sometimes, but yeah, it was just cool to see that it could in theory be done. I don't remember what they got as an actual solve rate for MNIST, or even if they checked average cell accuracy. Here, top accuracy 96%. L2. Okay. Anyways, and I think they did the accuracy thing basically by consensus. So even if it wasn't all fully colored in, they would just check the majority cells. So this is why I think they might be able to do the sort of problem that, like this one, but a lot more of the problems, yeah, like this one's actually kind of hard. Or, okay, not so hard. Again, there's some of them that are really hard, I promise. But this is effectively trying to construct a shape by joining all the red dots. I do not see how an NCA could do this easily. This is a lot more of a global task.
Right, right. So this is more like a translation.
Yeah, like, yeah, and it's not just translation. You also have to sort of be able to try, like, sort of, I don't know how to explain this. Like, I don't know. The way I would do it was I would, I think the yellow one is just the central one, so you don't ever,
yeah, the yellow one
the yellow one.
stays, and then the
And
other
then
ones are.
I would just take all the other ones out and then just, like, I'll try to put the blue one in and I try to put the green one in. And if that combination doesn't go, I just take it off and then try again. Just like iteratively, like just put the shapes together until it forms one cohesive, like bounded shape. And I don't know if a CA could do that. It would have to have a lot of memory to sort of store the shapes somewhere and then have a concept of being able to place them and remove them. But to be honest, if you look at the ARC leaderboard, a CA might not be able to do that, but oh, I mean, 16% is not bad, but neither can large language models. So yeah, I think everybody struggles with ARC-AGI 2, except somehow humans did better in ARC-AGI 2 than they did in 1. I don't understand where they got these pricings from. Did they actually pay people $17 per task? Anyways.
I have no idea. Interesting.
Yeah. This was always a confusing one. It's 17 cost per task, $17. I hope they weren't paying people $17 per task, especially for ARC-AGI 1. Yeah. Any other questions?
I have one thing to say.
Yeah.
Like, we were talking about long range dependencies. I ran a little experiment time ago by trying to create something similar to EM43, the simple emergent model with 4 states, but using an NCA. I used one channel, so it's and a particular way of encoding and decoding. But what I found is, like, it was able to extend, like, to propagate information like 5 or even 7 cells and not more. And this was for the vanishing gradient issue.
Yeah.
But I wasn't using the pooling method. I think it's very cool, the idea of using this pooling method that generates intermediate steps and breaks the gradient tree. In this way, you can truncate the gradients, and so they don't vanish. Like, you partially solve the vanishing gradient issue, because you generate this kind of mutations that are intermediate states that then get reused. I didn't use this, and without using this, I was able to extend it a few cells. One interesting thing I did is then, like, I tried growing it to move one cell, and then I retrained it, moving 2 cells, and so on. I was able to grow it to move for 10 cells, so a range of 10 cells.
So sort of curriculum.
Issue, yeah, so the issue, it's not foundational. Like, the issue is in the training. It's not that the model can't do it. It's simply, it's hard to train, because gradient-based training it's not it's not made for long-range dependency.
No, I would fully agree with this. It's yeah, there's also other methods you can use, such as like training into a critical state. So this is critical in the CA sense. It already gives you critical in the point-to-point dynamical correlation sense. It would already give you long-range dependencies effectively, or almost infinitely range dependencies. But yeah, so like you said, the truncation method does indeed, the pooling method does indeed basically truncate the long-range dependencies in such a way that it can learn to grow large shapes. I mean, if you look at the lizard, it's I think that you can grow a lizard that's effectively 100 by 100 pixels, so it can learn to communicate over 100 pixels. It just gets harder and harder, and the bigger the image gets, the sort of more pool, the larger the pool has to be to sort of keep all those intermediate possibilities. And then because the pool is so large and it's very varied, it sort of takes even longer to train, because it's seeing a lot of states that could be completely useless or quite useful. It also is more susceptible to something that's called pool poisoning. So what happens is that the CA, especially in the very early stages, creates an intermediary step that is very bad, like extraordinarily bad. So bad that when you feed it back into itself, when you sample from the pool and you feed it back to itself, it effectively produces NANs. And so then your pool has NANs in it. And then when you sample again, it produces NANs. And then these go into the gradient propagation for the NCA, which actually make it worse, which means there are more NANs in the pool, and it sort of explodes until the NCA doesn't actually know how to do anything. It only knows how to explode into not a number. And it's sort of a pernicious problem, because if you try and just remove those problems that have NANs in it, the training gets worse. Or problems that have very large values in it, the training gets worse, since one of the advantages of the pool is that you get to see a diverse set of states, and you're trying to converge from a diverse set of states into a singular response. So this is sort of what you see here. This is what the pool sees. Some of the initial states, and then a lot of like very, very diverse states. And then it's attempting to converge all the way into a lizard from those diverse states. So yeah, but I think sort of the pool training method has a lot of promise, because sort of accidentally, it's what the hierarchical reasoning model people did with their model. They effectively allowed their hierarchical reasoning machine to see intermediary states as well. And it's, according to the ARC Foundation, it was a big contributor to the improvement in performance. But the pool needs to be worked on. There needs to be better ways. I think there are some people had some interesting ideas of just looking at the batch and taking like the n worst the n worst outputs from that batch, and then rolling it backwards, so you actually keep every intermediary state, and then for really bad ones you just roll them backwards a few steps and then put them in.
Yeah, I think this method is also quite similar to some parts of the genetic algorithm, because you keep some survivors, like, and then you evolve from a different set of states, not only from one, and this allows for searching. Like, it's not a deterministic optimization; it's also a search. And
Yeah.
I think search is necessary for solving a lot of algorithmic problems. You can't do it with pure training in traditional sense.
Yeah, agreed. Any other questions?
Yeah, I want to ask you if you've ever seen this site here. I'm posting in chat. It's
Let's
sort
see.
of a task-based method for
Whoa.
solving it.
Welcome to. This is caped.
Caped or capped. Right. So I'm not sure who put this together, but I ran across the site the other day, and
Yeah, and these are the puzzle IDs.
uh-huh.
Yeah. Okay.
So like double click on one of those, and like it'll show a breakdown of like what it's doing under the hood. I think these are hand constructed, but they have like a set of primitives of like, look at this, look at the interior, measure the interior, I guess, yeah,
Yeah,
just
measure,
measure and fill.
fill. Okay, yeah. Measure, fill. Oh, that's really cool. Okay, then yeah, this could be, let's see, what's it doing? It's a cleanup, pad 2x, force more padding, clear, and then for each color, for each orientation. Okay, very cool. Yeah, this could be good for generating primitives for sort of NCAs to train on. Yeah, or
It's just a totally different paradigm. So it's like, I don't think that there's any automated reasoning going on here. It's just like humans are going in and filling out the steps to reason about each model, and then it's sort of you put it in the test case, and then like it'll reason through it using those steps, and it'll output
yeah,
hopefully the correct like yeah. So these are ones that are like solved, I guess. A lot of them haven't been solved yet, but
yeah. So I think what's interesting about this is this might just be so I know that Google is doing the same thing. So they put out a Kaggle competition on people submitting minimum length programs for ARC problems, because this is effectively what people are submitting for you, or a program that you can run step by step.
right.
Because at least Francois Cholet and the people who made ARC, they're quite convinced that program synthesis is the way forward for reasoning. And the people at Google are effectively, the competition is you try and solve every ARC problem with Python code, and you send the minimum length program, and the winners are the people who solve each problem with the fewest amount of lines. And I'm pretty sure they're effectively trying to generate data so they can train LLMs to do program synthesis like this on the ARC data set, which is sort of a bit funny to me, where they're trying to generate massive amounts of data of program synthesis to train an LLM to do program synthesis on a reasoning data set that is like spiritually, it wants you to use as little information as possible, But yeah, this is very cool. But as I like, this might be sort of the same thing. They're trying to gather as much information as they can on how to produce programs. Yeah, for each color, how to produce programs that do these things,
Yeah.
and then maybe train something to do it.
So I think they had like a set of primitive tasks as a library, and then
Yeah.
each program is made using those primitives. And then so you mentioned Kaggle training. What is that exactly?
So Kaggle is just a machine learning competition website.
I see.
So here, your machine learning dataset community. It's a machine learning community. People often, here you go. People often post competitions, and so there was one ARC Prize 2025. Oh no, that's just the prize. There's one posted by Google on this, and I think this is where they get the source. So the training set and the evaluation set, yeah. So the ARC prize is on Kaggle as well, basically.
I see.
Yeah, there's one posted by Google on Kaggle on effectively. They want this, what you just showed here. They want people to solve it via Python code, minimum length, and then so they can have this huge amount of data to train. On minimum length. I think it's minimum length program synthesis they want to do. Yeah.
From the chat, Brady is asking about the difference between CA, NCA, and EngramNCA. Can you elucidate that a little bit?
Yes. So a CA, just let's see, where did I put it? A CA stands for a standard cellular automata. So a cellular automata is usually described. I wish I had a better. I don't have a description on this, but it's usually described as a
Game of life,
n-dimensional lattice. Yeah, game of life is one of them, but it's a n-dimensional lattice where each sort of cell in that lattice can see its neighbors, and then based on its own and its neighbors' states, can modify its own state. And then you have a bunch of different things. So you have your neighborhood. It can be a Moore neighborhood, which is just like a square around the cell. It can be like a Lenya, which is like kernel neighborhoods, so long-range neighborhoods. It doesn't have to be a 2D grid. It could be a 1D. It can be 4D. There's infinite variations to this, but a CA, a cellular automata, is effectively like recursive local updates to a grid based on some rules. A neural cellular automata is one where you take the rules and you just turn them into a neural network. So if you look at Conway's Game of Life, those are like handwritten rules. You can implement them as like a lookup table, or you can even implement them as a convolution, all of these things, but like they're handcrafted simple rules. It's quite hard to search rule space for a cellular automata. So sort of a hack that, or like a shortcut that people did in 2020. So this was this paper, the Growing Neural Cellular Automata, was to just replace the rule sets with a neural network and learn it through gradient descent. So you can just learn the rules. And EngramNCA is effectively two CAs stitched together. So if you have a lattice that's H by W by N channels, you take, N minus X channels, and those are your sort of visual channels and hidden channels for a CA to do a bunch of computation with and to grow an image. And then you have X channels for storing sort of a tape that you make the CA dependent on, and then you just train a secondary CA to modify it. So EngramNCA is just two CAs stuck together operating on the same lattice, but on different parts of the lattice.
Is it limited to two? Or can you have like a bunch of them?
I think you can, in theory, you can keep expanding. They get harder and harder to train, but you could have three. You could split your lattice into three different sections. So, yeah. Again, by three CAs, I don't mean each shape is a CA. This is just the same CA creating all these different shapes within itself. It's just by two, I mean how you partition this part of your state space. So the channels. So, one of them affects these channels, and then the other one affects these channels. You could effectively make a third layer of channels where another CA affects those channels, and then you would encode a different modality of behavior. So you can keep stacking them like hierarchically, and you're subdividing your channels into that.
I see. So here, like if it sees green, it'll like make a gecko, and if like that one with the butterfly, that was a different color.
Yeah, exactly. So this one. So here it sees green, it makes a gecko. It sees red, it makes a butterfly. But yeah, but the sort of the compositional primitives of making the gecko and the butterfly are all this. So it's only constructing a gecko and a butterfly by just mixing these shapes together. It was
Right. So
effectively
like
we
here
were
the
just trying.
primitives are like the circle and the triangle and the square. For the
Yeah.
gecko, the primitives were different pieces of that.
Yes, for this one. Different pieces of the gecko. For this one, yes. For this one and the one with the butterfly, no. For the primitives were the triangle, the circle, the square.
Oh, okay.
And it constructs a gecko by just mixing them in a quite a complex manner to make a gecko. And it's the same thing with the butterfly one. So with the butterfly one, it's got the same building pieces as the gecko. So the triangle, the circle, the square, RGB. We've just told it, hey, when you see this, you use those three shapes to grow a lizard, and when you see that, you use the three shapes to grow a butterfly. So you're sort of recombining the same aspects. So this is what we're trying to do with your CA no longer encodes for sort of the shape like the lizard, what it used to be. It now encodes for basic behavior, and then you train another system to exploit that basic behavior to get more complicated results out of it. So it's almost like we've given it a paintbrush. We've given the CA a paintbrush now. It's like, hey, your paintbrush is now, you can use a square, circle, and a triangle of different colors. And based on what cues we give you, please draw something different. Yeah, sorry, I could have explained that better.
On the ARC,
yeah.
On the ARC prize challenge, have you tried like creating more examples for a particular problem? Like the ones that were like overfitting and like memorizing just like the 3 input problems.
Yeah. So I did. I augmented. Exactly. I went through the ones that were problematic and created more inputs. Some of them remain problematic, and some of them, with enough examples, it does start to generalize. But which gives some hope, saying, okay, maybe with a little bit more data or some augmentations to the problems, that are just general that you can do to every problem, you could get better results. Yeah, I think. But yeah, so I did try it. I just think it's outside of the spirit of ARC, of just like, hey, you throw at it more training data. I think that if you are going to attempt ARC, it really should just look at the examples like a human does and attempt to solve them. Obviously, you're allowed to pre-train to give them priors and biases, since humans have a lot of priors and biases that make ARC really easy. But once you actually go and attempt ARC, you should just only look at the problems. And augmenting them gives you a clue as to where your errors are. But what's funny is that you end up augmenting them with human biases. So you look at it and you're like, oh, I think I made a mistake because it doesn't have an example of this. So you give it an example of that. And so you're sort of giving it its own human biases by doing that. There was an interesting thing I did try, which was effectively augmentation. So with the standard ARC-NCA, it can learn its convolution filters. So these bits here, so these aren't sets, these are learned. And we were effectively learning 8 filters per channel. And then, the feed forward got 8 times the number of channels to see. A augmentation that has actually worked quite well, I haven't run all of the tests necessary, but it looked quite promising, is actually only learning 1 filter per channel and then applying 8 rotations to each of the filters. So the filters have to be useful sort of regardless of what rotation they're applied into. And it both reduces the size of the CA because you're only learning 1 filter per channel, and you're sort of dealing with a lot of the problems that CA's had of like it's hard to learn rotations and stuff like this in one go. And you can almost see it as an augmentation. It could be the same as teaching a CA to have 1 filter per channel and then just feeding it 8 rotations of the image.
Yeah, Brady on chat was asking about rotations. So that's what it would take to sort of augment that your architecture to have copies. So I mean, when you say 8 rotations, do you mean 4 rotations and 4 reflected?
Yeah. Effectively, yes. 4 rotations, 4 reflections. Yeah, just like 1, 2, 3. You can do partial rotations on a 3x3 grid, but it's not. You get very weird results. But
so
actually,
like
if you
growing a gecko that's like really big on the pixel grid, that's like tilted 45 degrees, that would be a little challenging.
No, actually, that's funny enough. It isn't. So growing NCAs. So if you go down here, they teach it to grow, like this, just in one orientation. And then if you go down to, there you go. They just multiply the sawballs by cosine and a sine. So these by this, and you can rotate the image. So it'll just grow a rotated version. So apparently that works.
Okay.
So yeah, by 8 rotations, yes. Like you said, I actually did do like rotations and mirroring, but you can indeed just do this and then just, split the rotation space into 8 buckets. But yeah, like the rules seem to generalize past that. I couldn't be able to tell you why. But effectively, I think it just sees the cells rotated. Like in the worldview of the CA, it just thinks it's been tilted. But the growing rules are the same.
Can you go up to the top of this and like grow something?
Oh, yes. Okay, so this is, wait, I'll slow down the speed so it's nice to see. And I'll pause it. So you start with a singular cell. And then.
So it started with a black pixel there?
Yeah, black pixel. And then, yep, there you go, black pixel. And then from there, it has to grow a lizard. And again, only local rules, trained on backpropagation, just on the lizard image. And if I speed it up now, there you go.
Now,
and then you can apply.
Oh.
Yeah, if you apply the rotation whilst it's grown, it doesn't work. And okay, so apparently not all rotations work. But let's try like 90 degrees. Yeah, that's not a problem.
Yeah, so that's aligned to the grid.
Exactly. I think if it's aligned to the grid, it's fine. And even if it's maybe slightly misaligned, no. Slightly misaligned is okay. No. Okay, no. So I think it has to be aligned to the grid for it to be okay.
Can you show an example of like where two of them are trying to collide?
Yes. So let me reset this. Yeah, so this is what would happen if you tried growing. Oh, am I even allowed to? Am I allowed to put 2 of them?
I think.
Click or tap the image to erase a part of the pattern. Well,
there we go.
There you go. If you try it. Yeah, if you try getting them to collide, you see if you get enough of them, they start acting really strange. Yeah, there you go. And especially, there you go. They can do very strange things. They're sort of fun generative AI models as well. So, I mean, to be honest, yeah, you can, yeah, there you go. It's just sort of stitches them together. Butterfly. You can get it to shift if you delete its head.
Has anyone tried to use this to simulate fluids, with fluid simulations?
CAs? I'm pretty sure in NCAs. I don't know if NCAs. I'm going to wager and say yes, that they've tried learning fluid rules through NCAs. I know that cellular automatas are used for, fluid simulations all the time. So, yes.
Yeah, because I was thinking, fluid simulations, like a lot of people tried to train neural networks, and in particular, convolutional recurrent neural networks, in order to match like the evolution of a fluid in time on a closed domain, and it worked pretty well. But it struggles to generalize like to slightly different cases from what was trained on. Like it's able to solve most of the issues, but it's not always stable. I think that the pooling method from NCAs would partially solve this, because creates the edge cases by zone.
Yeah, that's true. I think so. a bit of a shameless plug, but this is another paper me and a colleague wrote on general mass conserving dynamics for cellular automata. Oh, I just got sent something by Dugan. Yeah, this
Yes,
is
I
is
sent
that
you. This is something that we've been working on for a while. This is like, if you could show that on the screen. This is a fluid simulation on a hex grid where each particle is sort of modeled,
yeah.
and then there are collision rules
Oh,
for how these things bounce around. And
that's very cool.
yeah, yeah, it's work done by Nick here.
That's amazing.
Mm-hmm.
You guys could look into this then. So this is a paper me and a colleague wrote on general mass conserving dynamics for cellular automata. We basically just introduced a sort of a method that you can append to any cellular automata. So this is, we did it for like Lenya, here, what was it? Lenya, NCAs, and discrete CAs. And yeah, you can effectively simulate any sort of mass conservation. So if you've ever seen the paper Flow Lenya, they tried doing mass conservation CAs. What was nice about ours is that it effectively is 4 lines or like 5 lines of code that you append to your CA, and it does mass conservation in 5 lines of code. And so yeah, this is the Lenya one, and so these are like mass conserving. Actually, I don't know why I'm doing
I
that
guess that's like, you know, you have all these cells, and each cell has a particular amount of value contained in it, and
yeah,
you're just trying to
contained in it. Exactly.
preserve
And so
the
you're trying to,
global amount. Okay.
yeah, but this is both global and locally preserved. So you're not going to get mass jumping around.
Uh-huh.
So you get some, you know, pretty cool results from this. I think
So is it
this
trying
is
to
one with
preserve all 3 colors here?
wait, let me see.
I mean, if
So
there's
it's
more than one
either,
channel, for instance.
yeah, so if there's more than one channel, there's either preservation between channels. So, you know, all the mass in R is preserved, all the mass in G is preserved, and all the mass in B is preserved. Or there's mixing between channels. So I can go no cherry picking, low growth, cross channel. There you go. This is cross channel. So here mass is preserved in total, but can't move between channels. Here's another one. And this is just applied to Lenya.
Mm-hmm.
And then I think one of my Flow Lenya, okay, yeah, this was our example of Flow Lenya versus ours, but these were ones that I sort of manually evolved. So I just wrote a evolution simulator that you could click which results you liked. And this one just sort of looked like almost like dendrites, like neurons passing information along.
Yeah. That's super nice looking. I like that.
Yeah. Oh, here. This looks like almost like a fluid simulation. Oh, it's more like a chemical reaction. But yeah, so mass is conserved. And I think what you could do is that this works perfectly fine with neural cellular automatas. So NCA, here you go. This is it growing a lizard, but what we did was we put all the mass. So we calculated the mass of a lizard, and we put all the mass of the CA inside the first pixel and just distributed it equally across channels, RGB channels, and then let it just redistribute the mass at will across channels and across the image. So all the mass to grow the lizard was within the lizard when it started growing. And then these are some other ones on like sort of like growing biome-like things where the mass is conserved. Here.
Yeah, Brady is asking if something like this here, if they're competing for resources.
Yes, they're competing for mass. There's a limited amount of mass in the total system. So you can actually, this is one where we had death and resource accumulation. So the white dots are food. You can effectively, so if you find yourself over the food, your mass will grow, and you will consume that food. However, there is a constant decaying force. So your mass is constantly decaying. And so here you can see some sort of like, maybe not extrinsic evolution, but just, replication and a strategy to eat food. Yeah, and then I think this one was very cool. So this one, the strategy it learned was so almost like a mitosis. So here, when they die, when mass is being lost, they just leave it behind where they left it. On the other ones, when mass is lost, it reappears somewhere else randomly. But here you get sort of mitosis events. So if you look at where the arrow is, it's accumulated enough mass, and it just sort of splits itself. And there you go. You have a bunch of new creatures, and then this repeats itself like over and over again. So they just walk around randomly, accumulating mass, and then once they get big enough, it sort of just might like splits itself. So these are the sort of cool things you can do when you have competition for resources in a CA. So I believe this one was, yeah, so this one changed phases. So once the mass gets low enough, it changes into a phase where it sort of like moves around really fast, so it can gather mass again. And these are all
yeah, so
untrained
that's really
behavior.
interesting. So I guess like there's some very basic decisions that get made for these blobs.
Yeah.
So they have like a little bit of agency, and then the next question is, can that scale up? Like, can you get trends happening, or emergent behaviors coming out of some system like that?
Yeah, so I mean, you already sort of get a very basic form of emergent evolution within the bounds of the system, which is like you'll start with a high diversity of creatures if you just initialize it randomly in terms of all the channel spaces, and eventually it'll select for a single dominant creature. So you have to run these for quite a while. For those who don't know, this is Lenya, which is what this is based on. We literally just applied mass conservation to Lenya, is a generalization of Conway's game of life. And a lot of A-Life researchers are trying to see if they can find like the basics of artificial life within Lenya. And one of the constraints was it has to be mass conservation, which is what we were doing here. But I think, yeah, you can get emergent behavior effectively. I think it just needs to be scaled, like you're saying.
Yeah, or like competing behaviors or something. It's like this type of blob does this, and then this other type of blob does that, and then you see who wins. Or like predator prey.
I think
don't
so.
know.
Yeah,
Just thinking out loud.
No, yeah, I think so. I think so. The issues you would need, let's see this one. I think you just need a large enough scale simulation where you don't get a convergence to a singular blob that does one behavior really well. But I think with a complex enough set of rules and a large enough simulation, having this competition for mass would allow you to have sort of predator-prey dynamics. Maybe this one? Here. No, we don't have different blobs here. I think there was one where we had different blobs. There's, however, hundreds of videos, so it's kind of hard to. Yeah, this one's a bit like cells. Yeah, there's hundreds of videos in here. Also, go visit this if you want to see some all the cool videos. But yeah, you do get like, I think you will get predator-prey interactions. It's just you have to scale. If you look at biology, in a sense, it's billions, if not trillions and trillions of simulations going on at the same time. And here we're talking about a grid that's like, 1,000 by 1,000 pixels. So it's not very large. It doesn't allow for a lot of variety to appear. But the hope is by having this sort of mass conserving rule, we've sort of set the physics of the world. We sort of set the physics of the world. And now it's looking for a rule space that could exploit those physics so that you get sort of like emergent life. And then this was the final thing on this one. This is like Conway's game of life, but mass conserving. This is not exactly Conway's game of life, obviously.
Yeah. Yeah.
But it's yeah.
That's cool. So you still have like gliders and oscillators.
Yeah,
But
and
no.
here I think we gave them a tail.
Uh-huh.
Yeah, there's no vanishing. You start with a certain amount of mass, that's the amount of mass you'll always have. So,
Mhm. Yeah, so there's no
uh,
like generative guns, for instance, glider guns.
exactly. No glider guns. There's no like eaters, glider eaters, none of this. Uh, I think an interesting challenge if anybody's seen, you can make a computer in Conway's Game of Life with glider guns as signal generators and then glider eaters to toggle them on and off and all of this. An interesting challenge would be to make a mass conserving computer where all information you receive, you have to send back at some point to be able to transform and then send it again.
Yeah,
And it would
yeah,
be
that'd
interesting
be
to,
interesting.
like, I was curious in that Conway Game of Life version where you track the various trajectories. Would be interesting to see if it gets stable in time or if it continues to run. Like, does it ends to an attractor? Would be interesting to understand this. If it's actually energy conservation or only mass conservation emerging from this behavior.
I think it might only, I don't know, I think it might only be mass conservation. We didn't explicitly say energy conservation. There's an example of accidental, which one is it? Is it this one? This one or this one? Of accidental energy conservation in one of these, which is this one. We trained just one of the solitons to move to the edge of the screen. And what was interesting is it wasn't capable of moving without expulsing some mass in one of them. So I'm not sure. Also, the quality is terrible because these are like 500 by 500 videos. But often these like little moving solitons, they actually need to eject some mass behind them to be able to move. Maybe not because it's energy conserving, but because to create an imbalance in the rules so that they can move forward, they sort of have to leave something behind to create an imbalance. Because if they become perfectly symmetrical, they sort of just stay in place.
Yeah.
So it's almost like emergent energy conservation in the fact that you have to create a dissymmetry for movement to happen.
But in principle, you could have mass conservation without energy conservation in these
Oh,
simulations.
100%. Yes, 100%.
Yeah.
There's no limit on the energy, technically. You could have an infinitely accelerating. Well, I mean, no, there's a speed of light in these simulations, obviously. But you could have all of the mass eventually moving and then no energy was conserved.
Got it. Yeah, that's interesting. In a way, I feel grateful that we live in a universe where mass and energy are conserved. Kind of
I
simplifies
mean,
our physics a little bit.
I mean, if it wasn't, the universe would probably end very soon.
We just get
We'd
too
either
too
disappear into
busy too
nothing.
quickly.
Yeah, too hot or too cold, way too fast.
Yeah,
Uh,
yeah. If the sun
yeah,
was just pumping out unbounded energy and mass or something like that, it would just kind of fill up. Everything would just get overrun with an overabundance of energy, probably.
yeah. Anyway, that was a brief aside on mass conserving CAs.
Yeah.
I think those are always really interesting, especially the sort of the whole linear side of cellular automata research. I think it's very cool what everybody's doing there. But yeah, so
Yeah,
for
it's
what you were
super
showing
super
here,
awesome. I really like that linea. Yeah, this is so
yeah. So
this
is this
is
mass conserving or just energy conserving?
well, really it's the rules are mass conserving and energy conserving. Uh, what's happening in this particular simulation is we have a source on the left and then a sink on the right and then walls in the middle
Yeah,
that are rotating.
yeah,
So globally, we're injecting into the system more particles.
yeah.
Um, but
Okay.
to give you a sense of the rules, well, I'll skip that, but that's a topic for another live stream.
Yeah, it'd be great to see. Any more questions?
I think that's it. James, do you have any questions? Anyone on Zoom?
I suppose that's a no.
Oh, he typed in the chat. Did you
Oh.
discuss ARC Prize 3 attempt?
ARC-Prize 3 is a more of an agent problem. So if I, it's like playing video games. It's reinforcement learning, almost sort of thing. Have I tested out ARC-Prize 3? No. That would be an eventual goal, but I think you would have to
What
change
is
the
that
method.
challenge? What is that? I'm only familiar with like
Wait.
ARC 1 and 2.
Let me share my screen instead of just the page again, and then go to the ARC Foundation thing. ARC-AGI, where is it? Is it here? ARC-3. I mean, this describes it pretty well. It's basically just video games, like yeah, exploration, perception, plan, action, memory, goal acquisition, alignment. I wish they gave an example here, but I think maybe you can play it. Oh, there you go. Okay, press start. Where are we? Who are we? That's a good question. Okay,
What are the
these don't
inputs?
work.
No? Click.
Where are the inputs? Let's see, I can click and everything else is not allowed. So what if I click there? Nothing. 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 Okay, I think I've lost a little bit.
Maybe click the yellow square. Oh.
Oh, let's see.
Oh no.
No.
Okay. You have to click the those toggles.
So I think
click the red one until the yellow thing lines up onto the square. I think that's
there you go. Yeah.
It rotates the thing.
There we go. Yeah. So it's just okay, and then these cycle them. So you'd want to cycle this there and then cycle that there. And then you'd have to like probably like a shift register or move it to the right. Something like that. Like, you know, it's sort of like one of those shifty games. Yeah, so these actually get quite complicated quite fast. So like you'd have to plan ahead here. I put this here already, but that's not a great spot for it to be. Anyway, so yeah, this is ARC-AGI 3. Very difficult. I don't think NCAs are, or like the current version of NCAs, or like what I was doing basically has any chance on this. However, maybe, let's see, towards, what was it? The control, I think it was called. No. Card pull. Self-organizing control. There you go. Okay, this is another one on cellular automatas. On the card pull problem, this is very cool. Here are the inputs, so pull angle. So the cells are literally treated as inputs to the brain. Pull angle, angular velocity, card velocity, and they just repeat them just to give it some robustness. And then these are the right and left cell. So whichever one activates hardest, it chooses whether card pull goes right and left, and it can effectively control the card pull just using a neural cellular automata. So these are like local rules, things like that. So this is a neocortex view of a neural cellular automata, where the neural cellular automata, the cells are literally seen as cells in like a brain. And you can like, you know, poke this around.
So
And
I guess
it's quite robust.
the parameters of the system are input into the information channel, and then
Yeah.
as scalar values, I guess, and then
Yeah.
there's a CA that like organizes the
information into the center cells that do all the control. And so you can see sort of how the information is flowing here. These are some of the channels that you can see. Blue is negative, red is positive values. Yeah, so it's sort of like this is like a neocortex view of it all, of just literally pretend each cell in a CA is like a brain cell and try and get it to learn to do something. And so this might actually work for ARC-AGI 3, but you'd have to learn how to extract the correct inputs. But this is trained using DDQN, so double deep Q networks. Oh, here, yeah, input cell, observation, intermediary cell, and an output cell. So input cells are sort of blocked with only the observation going in. Intermediary cells have most of their channels open, and the output cells have most of their channels open. And then the zeros and ones here indicate to the CA what cell they are. And then it's just a classical CA training with DDQN. They did a bunch of experiments with like damaging it, introducing noise. It's quite robust to noise, to damage. Then they go over sort of like how information propagates. I did my master's thesis on improving this by effectively pre-training the NCA into a critical state and then letting it learn. And yeah, in the neuroscience context point of view, pre-training into criticality was quite a good improvement. Like it would train a lot faster and a lot more reliably. So yeah, this is sort of, I think this to me is the most interesting aspect of NCAs. I think their ability to simulate the neocortex might be the best thing we can get out of them. Instead of what I did here, like I said, it was quite canonical of just take the grid and then turn it into an NCA and just let it evolve in itself. I don't think this approach has much further to go. Maybe like 20-30% solve rate on ARC at best. I think there are better approaches.
Yeah, well, it was super cool how, where you were able to take this NCA technology and apply it to ARC. That, you got as far as you could.
Yeah, well, yeah, I think you could go further. I think
Yeah,
there's, but not much. I don't think there's that much left in it. But I do think, so I put this sort of at the beginning of the ARC-NCA one. This is a core belief of mine, not just about NCAs, but general CAs, which is their state. So their state affect the computation, and they can modify their own state. And so you have potential gradient-free meta learning. It is just the possible space of all CA or NCA parameters is huge, or maybe even infinite, and you have to find the exact one that gives you gradient free, or maybe there's a bunch, but it's a very small sliver of that state space that'll give you gradient free meta learning. But I do think it might be possible. Since they are capable of modifying their own state, and their own state affects their computation, and it's a sort of recursive loop of change your state, change your computation over and over again until you get a result.
So what is meta learning in this context?
Meta learning is learning to learn. Learning to learn, or the ability to learn on sort of like the task as well. So effectively, if I gave you two different tasks and you learned the first one and then you went to the second one and took some of the things you learned from the first one and applied it to the second one, but also learned the specifics of the second task, what you did there was sort of you meta learned effectively. You learned how to learn something.
Right. So, like for me, playing all these ARC challenges, 'cause I've been going through them myself, for fun and just for like mental exercise. Um, it's I can feel myself like doing that meta learning essentially, and what it comes down to is okay, I have like these particular things to look for as like a menu. It's kind of like that site I showed you, like the
Yeah,
capped one.
this one.
Uh-huh. And so it's like I'm building up like a repertoire of patterns and like tasks, um, primitives basically, and then
Yeah,
when I learn a new like challenge, I'm going through that index.
yeah, and you're effectively like you're like when you yeah, so when you like find something new, you're in your brain, you're effectively saying like, okay, I should look out for this sort of pattern or like thing that is happening now, since it can happen when I'm trying to learn what to do. So that's sort of like, what do you look out for to then learn what you have to do?
Mm-hmm.
Like um, it's sort of one layer away from learning. Machine learning programs can learn, but they don't really know what to look out for to know what to learn. Like, yeah, it's a bit confusing, but I think
I wonder
people will
if there
understand.
are things that computers are good at learning that humans aren't, and I wonder how like what's the simplest cases of those.
Hmm. Yeah, I mean, haven't some deep learning algorithms gotten like better than human, say like image recognition? Uh, like,
Yeah.
our visual systems aren't great. Or they're not the best in, like our visual system isn't even the best in the animal kingdom. And like it's sort of, I mean, the way I see it is that biology does good enough effectively. Like it served its purpose. We didn't have to be perfect visual interpreters. And so uh uh it sort of was good enough. And this is true for a lot of things humans do. Like, biology, as long as it's enough for you to survive and to procreate, it sort of stops there. It doesn't need to go much further. And I think yeah, a lot of like pattern matching things computers could effectively do better. Uh just because sometimes our own visual system isn't the greatest. So yeah, like I was saying, like I know some, or I think I'm pretty sure some AI systems got better than humans in Sci-Fi 1000 or something like that, where the images can get really confusing sometimes. And they're sort of finding strange patterns and biases to like determine something. Um, I think anything that's like huge amount of data crunching, a computer will do better.
Hmm.
So this is another thing. I think AIs might actually be good doctors, not in the sense of like doing an operation, but matching symptoms to a disease.
Yeah.
Uh, I think yeah, I think AI doctors could be better than humans. There's too much complexity in how medicines interact with different diseases and different medicines and all of this. It gets so complex that no single human can do it. But
Right.
I do
Right.
think
Yeah. They have
a
to memorize
sufficiently
all kinds of
complex.
stuff. So if it's
Exactly,
big
yeah. But
data,
I
then
think
like AI can really help.
exactly, yeah. AI is quite good at memorizing big data. I mean, effectively, I don't know if you guys have read this, but there's a paper from Google that effectively showed that LLMs are just a data compression mechanism, and that like these really large LLMs, all they've done is really just compress the entire internet, which is something a human can't do.
Right. Right.
So yeah, good. I think computers are generally better at uh, data compression and all that. Oh yeah, also lots and lots of medical literature to train on. Yeah, there's a lot of info out there. Yeah, I think anything that's pattern matching and data compression, AI systems are better than humans.
Well, um,
Yeah, just a final consideration I have in mind, like what Etienne showed with his work, what I partially showed with emergent models, is that like to move from pattern matching to true reasoning, you need to have recursion as the first thing. So mappings by its own can't reason, but mappings together with recursion and recursive mappings can extend this further. And if you can also have recursion in space, so kind of slide a window and have an infinite tape of memory to operate on, that gives another degree of freedom more to reasoning. And I think that the difference between mapping and Turing completeness. Turing completeness is something that can model any kind of algorithm in the sense that you can do recursion and use arbitrary memory on recursion. And I think this is the main thing it's needed for reasoning.
Yeah, I would also just say reasoning is a naturally iterative process. You explore, you go back. You know, you take multiple steps to reason on something, whereas, you know, a mapping is just in a single shot.
Yeah, and there are a lot of functions in the natural world that can't be modeled through like a closed form solution, like an equation that gets an x and outputs a y as a mapping, but can be solved with recursion and also arbitrary depth recursion, and also arbitrary largeness of the state you operate on.
Yeah.
And yeah, effectively, neural cellular automata are doing this because they use convolution and recursion.
A lot of work to be done on the subject of understanding tasks.
Yeah. It's
for AI agents.
Yeah, I would agree. It's I think we haven't cracked the reasoning problem yet, even if we call current LLMs reasoning models. They're effectively just state space conditioning with their reasoning tokens.
Yeah, super interesting. All right, thank you, Etienne, for coming on. Thank you, Giacomo, for joining us. Thanks to everyone on the live stream for tuning in.